Okay, did I have, no, my volume is muted. So we're gonna do the worksheet. It is on, let me share screen, show where it is. Go away. Come on. There we go. We go into Canvas, it's into the unit 2. I just posted it there. So if you're online, that's where you can find it. But instead of me writing up all of the word problems, I figured we'd have them all in a sheet and kind of work towards some of these. I think that'll be less hassle for everybody, hopefully. If we have anybody else come in, there's some there. Okay, so this section is really just dealing with optimization. We're going to take that first derivative and second derivative test and use those. So, when are they useful? We're going to do this. Okay. The first one on here requires a picture. I didn't have a quick way to type the picture up into the note file. So there's our picture. Okay, I'm just going to go for it. So we have a rancher with 400 feet of fence, and he or she really wants to make a corral, like a little yard thingy. One side of it is a barn. Let me flip this so I can write on it. And the other side, and we don't have to put a fence by the barn because that counts as our fence. There's 3 exterior fences and then 2 interior ones. So we're separating our space into 3 different little areas. We want to optimize our area inside. So, any thoughts on how to do that? What does?
We had to make an equation.
Uh-huh.
Equals 400, but okay.
Okay.
We're gonna have 2 sets of variables, one for the outside and or one.
They'll end up being 1. Okay, but what part of our little barn situation here needs to be 400? Yeah, that's what I was trying to. Yeah, so all of our friends. So if we take, how many X's do we have there? Okay. That's not the equation we're going to optimize though, because what are we trying to optimize? Area. Slow down. We will take the derivative, just we have to get our equation first. So if we're going to optimize area, that says I need the area equals length times width, which will be X and Y for our case. So we want to maximize this. So for a lot of these, we're going to have to come back, remember our area equations, some volume ones, so your cone, your cylinder, all those fun things. All right, so I'm going to call this my width and this my length. So width equals X, length equals Y. But if we have an equation with an X and a Y, that makes it a little messy to solve. So that 4X plus Y equals 400 is very important because now we can solve this for Y and we can express Y in terms of X. So this gives me Y equals negative 4X plus 400. Okay. Now I have everything I need to plug it in my area equation. So the area of our yard here will be length, which is negative 4X plus 400 times my width, which is just x. Now, as you mentioned, we need to find the derivative of this because we want to maximize our area. And if we look at this, we know we're going to get a parabola. And we know the basic shape of this. So the details are going to be a little foggy, but we know in general it is an upside down parabola. So if we find a critical value, that's going to give us the maximum in this case because we know the shape. All right, we should be really good at finding derivatives. At least I hope so. So find a derivative. I get negative 8x plus 400. Okay, set it equal to 0. Solve for x. I need to squish this a little more. So now I have my x value. But that doesn't give me, we want the dimensions of the area and the actual area. So I know my x value, I know my width. How do I find my y?
Correct.
Not quite. Yeah. We're going to plug it into that length equation. We have a lovely equation for there. We might as well use it. Oops. Scoot this down. I get negative 4 times 50 plus 400. That should be negative 200. It's 400. So I get y equals 200. One, two, three zeros. All right, that, come on, gives me 10,000 cubic feet of yard space. Not cube. It's been a long day, friends. Square feet. It's more like it. Now it's always good to come back. Do our proportions work and does this make sense? Let's change to blue for this. If this is 50, this is 50, 50, 50, and this down here, this whole piece is 200, and we add that up, do we get our 400 fence? Yeah. 50 and 50 is 100, 2 more 50 is another 100. Yeah, we get 400. So for a lot of these problems, we can actually check them with our original data and make sure they work. So our dimensions are 50 times 200 feet for 10,000 square feet. When it's a parabola, it's really easy. We know exactly which one has to be the max or min based on the function we're looking at, if it's right side up or upside down, and we're done with that. All right, does that follow? Does that flow? Make sense? Number 2, we are going to get through this worksheet faster than I thought, maybe. Okay, suppose an airline policy states that all baggage must be box shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-based box with the greatest volume under these conditions?
Sixty-four rolls next time to the side. Okay.
Okay. So we know the length plus the width plus the height has to be less than or equal. So we're going to say we want the greatest. We're just going to put equal 64. Technically, it should be less than or equal, but we're gonna fudge it. We have a square shaped box. Square based box, excuse me. I always like to draw a picture. If nothing else, I have a nice picture to look at. So I'm going to use I like X as my variable. I'm not going to need a Z, but if I needed a Z, I'm using that. Are we solving or are we just writing? Drawing. Okay, I'll give everybody a second. So we know the base of this is a square. So I'm going to say this is X and this is X. Since it's a square, both sides are the same. We don't have to bust out another variable. The height doesn't have to be the same as the length and width. We're going to find out it's going to be, but it doesn't have to be. So I'm going to call this height Y. So length equals X, width equals X, height equals Y. And why do my X's always look like Y's? We're maximizing volume, so we need a volume equation. Length times width times height. And so volume equals X squared Y. But we have a Y again. So let's come back to this formula. X plus X, whoops, time plus Y equals 64. So now we're going to rewrite this as 64 minus 2x. I highly recommend writing down a lot of these things. So, okay, I know this equation, it's probably going to come back into play. So let's get our X plus Y sort of thing. What's our volume? Okay, if I don't know how to make it into one variable yet, put it into two and see if you can get rid of one of them. Okay, clean up and then derive. 64x squared minus 2x cubed. I'm going to try to fit this whole thing on one page. We'll see if I'm successful. V prime. Yeah. Okay. I get 128x minus 6x squared. Set it equal to 0. Interesting things are going to happen on this. That is not divisible by 6. No. 64 minus 3x. Yes, thank you, task manager. Go away. It'll go away when it wants. So I take my derivative, I get 2x equals 64 minus 3x. Set them both equal to 0. Bring that up here. Hey, go away. Thank you. Before I do any more, I can throw out one of these two things. Yeah, if our width is 0, we don't have a box. So I know that is not going to maximize my equation. So I'm just going to leave that there. All right, so the other one, do a little flippity floppity. I get x equals 64 over 3, which is 21 and a third. Okay, good. All right, so I get my dimensions are 21 and a third for those. And my last one, bet it's going to be the same. So 64 minus 2 times 64 over 3. Did we get the same? 21 and a third? It says inches. Not feet. Okay, so I have the dimensions of my box. What's its volume? I'll get my calculator. I can't do that math in my head. Oh, I can fit the whole thing on one screen. I'm so proud. So I get 9,700 and change as my max volume. So yeah, 2 feet, 18 inches, so there-ish. It's a pretty big box. You're going to find your optimal shape is a regular shape. So meaning a square versus a rectangle, a circle versus an ellipse. We all know what an ellipse is. Okay. An equilateral triangle versus any other type. So your regular shapes are what you're likely going to go towards. Those are your best bet. And yes, squares are rectangles, right? We cool with that? Okay. I have this fight every year with my kid that a square is a rectangle. I've yet to convince him, despite having, I don't know, like 30 math books in my office. He doesn't believe me.
X equals 0 can't happen because you can't have.
Well, yeah, because then, I mean,
Sense.
yeah, even if it's just paper thin, that's still not 0. It's functionally 0, but it's not 0. And then if we were to come up with a negative solution, we would throw that out too, right? Because we can't have negative area. Yeah. Yeah. All right. Are we good with those two? All righty. Number 3. All right, these are where it gets a little weird. A rectangle is constructed with its base on the x-axis and two of its vertices on the parabola y equals 16 minus x squared. What is the dimensions of the rectangle with the maximum area, and what is its area?
Say again. 2 points.
Yeah, in this circumstance, yes, it's a corner. Yeah. So first thing, draw the parabola and see what it looks like. I'll do it in a minute. It's easy to watch me draw them. You do your own. And no, Desmos doesn't count in this case. Yeah, vertex is the singular, vertices are plural of it. Four is gonna be its, yeah. All right. Each of my tick marks here are 2, just so I don't have to draw up to 16. So we're gonna have x-intercepts of 4, -4, your y-intercept is 16, and do your very best to draw a parabola. All right, did your parabola more or less look like that? Hopefully, yeah, no, did we not draw a parabola? Wider. Oh, it's okay. It's a sketch more than anything. The important thing here is to note its maximum, which we see is 16, and its x-intercepts. So if we get x-intercept, or if the width of our rectangle is bigger than 8, we've made an error. And it's probably going to be closer to the 4 mark, all things considered. All right, I am going to draw a rectangle that is probably not optimal, but so you can see what we're talking about. So our rectangle hits here and here, here and here. And we want to find it. This is the inside, because I feel like coloring to them. I don't know, personally, I always had trouble with these because I had to visualize it and it took a while to figure that out. Okay. We need to figure out our 4 coordinates. Really, we can figure 2 of them, the right side, and then just mirror it over and we'll get the left side. So we want the maximum area. I'm going to call my width goes this way and my length goes this way. It really doesn't matter, but so we're all on the same page. Let's all do it this way. If you want to do it the other way, just to be obstinate, you do you, but this is what I'm going to do. Okay. What's the width of our rectangle? We don't know. It could be 8, but probably not, because that would be a very flat rectangle in this case. Well, can you give me the length, the width of my rectangle in terms of X or Y? The width, we're looking at width. Yeah. So we don't know, let me pink again. We don't know what that distance is, except I know it's X. And I know this distance on the other side is going to be the exact same thing since the rectangle. So the width is 2X. The harder part, I think, what's the length of our rectangle? So where does this happen? You think about it, our X variable, our width is on the X axis. So the length has to be on the Y axis. So what is that point that my little pink mark is kind of pointing to? What is that ordered pair? Kind of a, no, what is the ordered pair? How do we figure out what that point is? It's on my parabola, right? Okay, what's the equation of my parabola? Yeah, so if this point here is X, this dude up here is just gonna be X, comma, 16 minus X squared. We don't know what it is, but we know what it is in terms of X, because that's our equation. So the length now we find the area again.
It's can't be the same. Or negative. Just
We will. So your Y is always positive. The Y value is going to be the same. We just need the length, the height anyway. The X value, yeah, over here, well, with respect to me, over here is the positive, here's the negative, but they're going to be the exact same thing. We find one, we have all of them. Yeah, yeah, something to think about. All right, area equals 2x times 16 minus x squared. Interestingly, my area equation is a cubic function, not a square. Just kind of happens that way. Find a derivative. I really want it to be 8, but it is 6 again. Bring that over. 6x squared equals 32. X squared equals a yucky number, 16 over 3. Take the square root of that. X equals plus or minus 4 over root 3. So square root of 16 is 4, square root of 3 is root 3. If we want to rationalize the denominator, we just multiply top and bottom by root 3, and that's what we're going to get. In this case, the negative works out for us. We do need a negative because we're coordinates. So this x value is 4 root 3 over 3. And this one is negative 4 root 3 over 3. And what's my y value? I have everything on the screen to figure out y. I'm going to put in the non-rationalized version because it's going to make the math of this a little easier. old people with beards a long time ago said we couldn't, and nobody's argued with them since. I don't care, but the old dudes with beards says we can't do it, so we don't do it. So I'll leave this all on the screen. I don't know why. It's a holdover probably from pre-calculator days. I just like to blame old dudes with beards because they can't defend themselves. So, because they're dead. Okay. So I have my X and I have my Y. Can you find the four vertices of your rectangle? All of the data is on the screen. You don't even have to calculate anything. You just have to find them. If you want to be lazy, you can write it as 2. Okay, so do I have some vertices? Uh-huh. Negative. Yep, I'm going to put it as plus or minus, but yes, it's exactly right. And the other vertices, it's actually pretty similar. And my Y value was 32/3. Last question on this one. What's the area? You're close, but not quite.
X squared.
That's good. 2x. Yeah. Yeah, because what you gave me was the right half of my triangle, our rectangle. We have 2 sides, so don't forget we have to double it. So I get 2 times 4√3/3 times 32/3. I'm not doing that in my head. 8 times 32 is 256. √3/9. Can I divide that by 9? Oh, I cannot. That's our area. So my best advice on these is to draw a picture, come up with your equation like that you want to maximize and say, okay, what other data do I have? Can I write my X or Y in terms of the other information? You're typically going to have 2 equations. The one you want to maximize or minimize, and the other one you want to use to put it together. Okay. I'm going to give everybody a minute to think about 5 or 4 and 5. We have 2 positive real numbers whose product is 50. What is the smallest possible sum we can get with that? And the other one, we have 2 non-negative real numbers whose sum is 23. What are the maximum and minimum values of a squared plus b squared we could get? So see if you can come up with some ways to solve this. I'm going to pause the video so it's not dead air when I post it. recording. Okay. So number 4 says what two positive real numbers, so they can't be 0 and they can't be negative, whose product is 50 have the smallest possible sum. So my numbers, X and Y. We have the product of X and Y is 50. And the sum, call it S, equals X plus Y. We want to minimize the sum. Do we want our equation in terms of X or Y? No, that's why I asked. Oh, all right. So X equals 50 over Y. So I'm going to solve my top equation for X, plug it into my minimizing equation. So S equals 50 over Y plus Y. That's going to make my derivative a little easier. We're minimizing the sum. One of those is going to go away, one is not. So S prime is negative 50 y to the negative 2 plus 1. We're going to set it equal to 0 again. Okay, I'm going to rewrite it as the denominator now. Add the negative 50y to both sides, or y squared rather. We already know y can't be 0 because it's a positive real number. So I don't even need to note that. If I get a 0 out of here, we throw it away anyway. So we're good here. Get my y out of the denominator. So multiply both sides by y squared. I get 50 equals y squared. Y equals plus or minus the square root of 50, which is plus or minus 5 root 2. I can throw one of those away, can't I? Negative. No, I don't even need that. 5 square root of 2. So now that I have y, come all the way back up here. What's x have to be? We're going to get 5 root 2. So that minimizes our value. It's usually going to happen that your values want to be really close together. And a lot of these things, it's either going to maximize or minimize stuff. All right, we have 2 more on the sheet. We want to have 2 non-negative real numbers, A and B, whose sum is 23. We want to maximize and minimize A squared plus B squared, whose sum A plus B equals 23. All right, so A and B are non-negative. that means they can be zero. So that's what non-negative means. You just can't be negative. Easy to mix up. I'm gonna solve everything for A because my A's tend to look like other numbers. My B's are usually pretty distinct. It's the only reason I'm making that choice. So I say A equals 23 minus B. Gonna plug it into my, we'll call it a Z equation because why not? 23 minus B squared plus B squared. I'm going to do the chain rule, but it really doesn't matter. You could expand that 2 times 23 minus B times -1 plus 2B. So don't forget your B is negative on the inside, so you have to multiply by its derivative, -1. Now it's pretty much the same problem we've done 4 times before. I'm going to expand this now, -46 plus 2B plus 2B equals 0. 46 equals 4B. And B equals, we get 23 over 2. So is that a maximum or a minimum value?
So for zero,
Not necessarily. How do we figure that out? There's 2 ways we could figure it out easily. There's 3 ways we can figure it out easily. I wouldn't do that. Well, how do we, based on derivatives, how do we know if something's a max or a min?
plug in something. It goes from
Yeah. So if we do our test values, here's my 23 over 2. If it goes increasing, decreasing, that's a maximum. The other way, it's a minimum. The other way we could do this, half it. So what does this look like? Actually, you know what? Desmond's time. I don't want to draw it. Z equals 23 minus x squared plus x squared. Oh, you want a y, don't you? Fine. Where'd you go? Did I make a big error on this? There it is. Oh my goodness. So what do you think? The value they gave us, is that a maximum or a minimum? Yeah, we're a right side up parabola, so that's gonna give us the min. How do I figure out the max? What is the min? Let's go with that. We're minimizing that. Um, so that means 23 over 2 squared, two of them really, and squared, it's 2, 529 over 2. That's our minimum value we can get for the squares. How do we come up with a maximum? Well, we have to be non-negative, right? So what is the biggest value I can plug in for 23? Same for B, really. And so the smallest thing I can be a 0. So what does 23 squared give us? Okay, so the biggest value I can get for that is 23. So A squared plus B squared equals 529. Adjust it a little bit. Make A 22 and B 21. What happens then? I 1 rather. What? Now we are. But not for the point that we were given. We're using logic. Because my gut tells me that it's going to be 23, but let's see. 22 squared is 484 plus 1. It is not larger than 529. That's a greater than with a slash through it. So as we get closer to the vertex, I see you. As we get closer to the vertex, we get smaller and smaller. As we get farther away from the vertex, we get bigger. Can we get any farther from the vertex than 23? No, because then our A is the biggest it could be, our B is the smallest. This can't go anywhere, so it always has to be 23 is as big as we go. So really we're saying, okay, I think it's this, but let's test a value and make sure. So, I mean, it's kind of guess and check, but with a hefty dose of logic.
Boundary 0 to 23. So if you want, you just keep guessing, eventually you get doing answers. And then you just start with your max and min, and you just work your way down.
That's a lot of guessing. That's an infinite amount of guessing.
You can make some good, like, you can clearly tell it's gonna be a whole number.
You hope. Okay. We have one more. I bet you can do this one by now, but we'll do it together. So I don't know, the moral of that story is sometimes the answer isn't clear by the calculus. You have to look at the graph and think about what are your outcomes. Okay, we have boxes with square bases and a volume of 100 cubic meters. What one has a minimum surface area? So the volume equals a height times my base squared, since the base is a square. And we know its volume equals 100 meters squared cubed. Now we need to find the minimum surface area. I haven't done any of these yet. So I'm going to draw my box exploded. So you know how we could draw the box before? I'm going to rip it apart. What does the base of my box look like? Whoops, it's a square, right? Because it said it's a square base. So the dimensions of the bottom are b by b. Guess what the dimensions of the top of the box are? What is one of the sides of the box looking like? You know, at least one of the dimensions.
Well, yeah. Side?
Yeah.
Can't be 12. We don't have the height.
But we can talk about in terms of the height. So we don't know anything yet, but we can make some. The base is going to be B, the bottom of it. The height is H. Since we have a square base, all four sides are exactly the same. I don't want to draw them all out. So the area of this guy is B squared, as is this one. Its area is BH. And there's four of them. So my surface area, 2B squared, yes, plus 4BH. Mm-hmm. Yeah. Well, as long as the bottom is a square. If the bottom's not a square, we're going to have top and bottom will still be the same. You'll have two pair of sides that are the same and the other pair of sides that are the same. But in this case, they were nice to us. Okay. We again have extra variables. I'm going to get rid of that H. Yeah, because my B is squared. So I know my volume is 100, and that equals H times B squared. So then my H has to equal 100 B to the -2, divided by B squared, whatever, B to the -2. Plug that in over here. So my surface area is 2B squared plus 400 B to the -1. We all see why that's B to the -1. You just talk before you think sometimes. Okay. Yeah, so I'm plugging in for B. I get 4B over B squared. Cancels one of the B's out, one comes up. Guess what we're gonna do? Take a derivative. Seriously, in calculus, when in doubt, just derive something. Almost there. We know B can't be 0 because we're dealing with real items. It has to have a shape. And hey, as you said, what's the base going to be? And we can back solve. We're gonna get the height as the same amount. So moral of the story is most things are regular. You're gonna find many circumstances, the regular shape is the best one. Now, when you have other constraints and other weirdness going on, that may not always be the case, but a lot of times. Excuse me. Okay, that's really all I have for today. Did the worksheet sort of thing work? Was that good? So we didn't have to like look up and down and see my scrawling handwriting? Okay. When we do word problem sections, I'll try to do this again. Just also have some like ready to go. All right, I'm gonna take a minute to save my stuff. If you need me, I'll be here. If not, I'll see you Thursday. I don't know what day it is. Never know what day it is. Bye, online people. You can't see me waving.